Okay, let's get started. Welcome everyone to today's PacTrans webinar featuring Vikash Gayah on perimeter metering control for two-region urban networks using deep reinforcement learning. Before we get started, I would just like to run through a few quick logistics for anyone who is not familiar with Zoom functionalities. So we have three ways that you as attendees can interact with our presenter today. The primary two ways would be the Q&A box, which you'll find an icon for at the bottom of your screen, and a raise hand icon, which you'll also find at the bottom of your screen. So as questions come up during his presentation, please feel free to post those in the Q&A box. You can see what other people have posted as questions. You can upvote questions that you like and want to hear answers to. And you can also, if you would rather, save your questions till the end, and you can hit the raise hand feature and we can enable you to verbally ask your questions or share your comments. So those would be the two ways. And then we do have the chat function available for you to communicate with panelists. We would ask that you reserve the chat box more for any technical issues you're having, and direct your questions to the Q&A box if you're gonna write them down that way. The video today is being recorded, and we will post that on the PacTrans YouTube channel probably early to mid next week. So if you know others that you'd like to share what you've seen with, we would encourage you to do that. You can pay attention to our YouTube channel there. So I think with that, I will introduce our director of PacTrans, Professor Yinhai Wang, who is a professor of civil and environmental engineering at the University of Washington, and I will let him share his words of welcome and introduce our speaker today.
Thank you, Cole, for the introduction. Hello, everyone, and welcome to this PacTrans-sponsored University of Washington webinar. This webinar will focus on perimeter metering control for two-region urban networks using deep reinforcement learning. You know, network control is a very classical topic in traffic engineering. Deep reinforcement learning is a new method. Let's see how we combine the two and show the power of the new methodology. Our speaker today is Dr. Vikash Gayah. He's an associate professor in the Department of Civil and Environmental Engineering at the Penn State University. He got his bachelor and master's degree from University of Central Florida and his PhD degree from UC Berkeley. Dr. Gayah's research focuses on urban mobility, traffic operations, traffic flow theory, traffic safety, etc. He's a very busy guy and serving at multiple journals editorial board or advisory board. That includes Transportation Research Part C, Part B, IEEE, Intelligent Transportation Systems magazine, etc. Dr. Gayah has been working on traffic flow and control related issues over the past many years, and he built a lot of credentials in this topic. So we're happy to get him to speak to our webinar audience today. So now let's welcome Dr. Gayah to start his webinar.
Well, thank you so much, Yinghai and Cole, for helping me organize this and for inviting me to give this webinar. Really appreciate it, and thank you to everyone who's attending. I mean, it's I guess a Good Friday, so happy Easter to everyone. And you know, I really appreciate you taking your time out of your busy schedule to hear about the work that we're doing. So with that, as both Cole and Dr. Wang mentioned, I'll talk about perimeter metering control using deep reinforcement learning. So before I get into the meat of the presentation, I just wanted to acknowledge the people and organizations that made this work possible. So the work wouldn't be possible without my PhD student, Dongchen Zhou. He's the main contributor on this work, and he's done all the heavy lifting. And I just get to take the credit. So really appreciate that. And then also wanted to acknowledge the financial support of the NSF and the Penn State Institute for Computational and Data Sciences. So with that, I can go ahead and start the actual meat of the presentation. And so this work deals with using macroscopic fundamental diagrams to model transportation networks. And so it turns out, as most of us know, if you're dealing with urban transportation systems, they are incredibly complex systems, and that's primarily because they're made up of so many individual pieces. So if you were going to model, a downtown urban network, this is a picture here of San Francisco, just a small portion of San Francisco. It's made up of many, many component pieces. Those are like the links, all those individual red lines and the nodes where those links intersect. And so if I wanted to model realistically, the behavior of vehicles on this system in order to design a traffic control strategy to improve traffic efficiency, I would need to model each of these component pieces. I would need to know, what's the free flow speed or the speed limit on each, the capacity of each link, the length of each link. At the intersections, I would need to know how the intersections are controlled, the traffic signal timings, things like that. If I was going to use a simulation, I'd have to model the behavior of every individual vehicle or agent traveling in that network. And so it turns out, that takes up a lot of computational resources. It's incredibly complex, all those interactions. And so as an alternative, if I really didn't care too much about the distribution of traffic on each individual link or where the vehicles were exactly, but instead I wanted to model the system as a whole, we can rely on a new paradigm that ignores the details of what's going on at the individual components and just focuses on the aggregate behavior of this entire region. So by aggregate behavior, what I mean is, I just want to know like how productive that specific network or region of the network is operating. If I focus just on that, I don't care about the distribution or the exact location of individual vehicles, but if I kind of know something about the distribution of those vehicles and distribution of origins and destinations, I don't need to know, exact details about everything. If I can do that, then I can divide this network, I can look at it as a region and I can model the behavior of the network just on that regional level. Now, this requires that vehicles are relatively homogeneously distributed across that region, and that's not always met. But that's not really that burdensome of a problem, because then we can just divide the network into smaller regions in which the network, those individual regions have that sort of relatively uniform or stable congestion pattern, and model the system as a system of a few or a handful of individual regions. That makes use of the existing well-defined relationships between traffic parameters at that regional level, specifically the productivity of the network, which we can define in different ways, but it could be the flow, it could be average flow, it could be the vehicle miles traveled in the region, the rate that vehicles complete their trip, or just some sort of measure of how productive the region is, and the level of use, how many people are traveling in that network. And so it turns out that actually, when I started my PhD in 2007, my advisor, Carlos de Ganzo, sort of proposed that there are these well-defined relationships that exist between that productivity and network use measured at a regional level, and that it is well-defined and reproducible. And so if that exists, and we've, since, in the 15 or so years since then, we've sort of learned that there are these reproducible relationships, and we can then leverage that information for this regional level modeling and control of urban traffic networks. If they exist, again, it takes that very complex network with like hundreds of links and hundreds of nodes, and we can simplify it into a fairly complex but much simpler system with a handful of regions. And I just need to model the flow of vehicles going from one region to the other to simulate the overall evolution of traffic in that system. Why is this useful? These MFD-based modeling frameworks have been used to develop different types of regional traffic control strategies. So I didn't mention before, but that those well-defined relationships we call macroscopic fundamental diagrams, analogous to the traditional fundamental diagram for a link. This is a macroscopic or network-wide fundamental diagram for an entire region of a network. And so we've been able to use these MFDs to study how to control systems from a regional level. And that's led to the development or refinement of different traffic control strategies. So one example is congestion pricing. We charge vehicles to enter a downtown or a specific cordoned area of a network. This is going to be implemented in New York City in the near future. So how do we set those prices? We could use that MFD-based framework to understand what is the impact of different prices, or to determine the optimal prices at any point in time based on the actual congestion level in that cordon region. Another question that's been answered with this approach is space allocation. If I have multiple types of vehicles, so cars and buses, for example, or cars, and I need to dedicate some space for, Uber pickups and drop-offs, urban freight maneuvers, and so I want to dedicate that, take that away from cars, we can use these MFD-based frameworks to figure out what is the optimal distribution of space allocated to different modes. And that's been done in the research literature as well. I've actually personally used this type of framework to answer, I think, more practical questions like street network design. Just as a side note, I grew up in Orlando, Florida, where the street network is made up of one-way streets. I personally hate one-way streets. And so I used this to study what is the operational efficiency and the differences in operational efficiency between networks that are made up of one-way streets compared to two-way streets. And that's actually led to the development of different types of street networks that might be more efficient than either of these two that I'm showing here. And there's also been some work on vehicle routing, but from a regional level. So, normally the vehicle routing problem is like, I have a vehicle going from one origin to a destination. What are the sets of links that the vehicle is taking from the O to the D? We can look at that from a regional level. What regions are you traveling between your origin region to your destination region? But the most prevalent example is actually what's called perimeter metering control. And so what perimeter metering control is basically limiting the rate that vehicles can enter a congested downtown region in order to help it operate more efficiently, okay? So this is my example here. That green circle is the downtown cordoned area. Instead of charging a price for vehicles to enter, we simply limit how quickly they can enter that region using traffic signals. And so the idea is to do this in such a way as to keep the downtown cordoned area from getting too congested. If you remember that MFD-based shape, as accumulation increased, the productivity of the network increased, but then up to a point, and it had a maximum value, or the capacity of the network. And then after that, it got congested, it got less and less productive. And so if we let too many vehicles into the downtown area, the network becomes congested because people are running into each other. They can't get to where they're going. It takes longer for them to get out. Congestion builds, congestion propagates. And so in order to alleviate that, we can simply say, hey, instead of going into the downtown and congesting it, why don't you wait outside, okay? And in some cases, we can keep vehicles waiting in places that they will not contribute to congestion. So for example, New York City is a great example. Big long bridges and freeways entering downtown Manhattan. There's a lot of queue storage spaces on the bridges or the freeways that are feeding those bridges. And so vehicles can wait there where they're less damaging than waiting in the city streets. It turns out that even if they have to wait in other city streets, they're waiting outside a cordon region, but that waiting outside is still in an urban environment where they're contributing to congestion. This sort of perimeter metering control can still make the overall productivity of the network higher, can still reduce travel time for all vehicles if applied intelligently. And so there's a lot of perimeter metering control strategies that have been developed using this macroscopic fundamental diagram approach, looking at this regional traffic dynamics. The problem with the existing, or not necessarily a problem, but a challenge, I guess, with the existing approaches is that they require detailed knowledge of that functional form of that network's MFD. So you need to know that curve, what it looks like. And you need to know the underlying traffic dynamics, how vehicles move from one region to another. And if that's known, there's existing methods that work well. The most common is called modeled predictive control, and it requires these dynamical equations. It requires the MFDs, but if we know that, we can control this in an optimal way. There's also feedback-based methods where we say, okay, well, we just know that we want this region to never exceed a certain critical accumulation level or not get too congested. If it's too congested, we just force people to wait outside. If it's not congested enough, we let people in as quickly as they want to. But that requires that we know what those critical set points are. And that's actually, if I have a single region and that I want to protect, very easy to do, very well known. We can feel comfortable doing that. But if I have networks made up of multiple regions, I don't know how to set those thresholds that's best for the entire network. And so that becomes a problem. And then there's also some model fee approaches that have been suggested in the literature, but they still require that we know what those set points of congestion are. And again, in a single region, I can kind of know what that is. The accumulation associated with the network capacity, its maximum productivity. But in multi-region networks, I'm less likely to know what that is. Further complicating this is all of this information that I'm mentioning that's needed is fairly difficult to obtain. Many studies have been performed to estimate actual MFDs, but few studies have actually done it using empirical data. And actually in the United States, to my knowledge, there have been no MFDs estimated in the United States using empirical data. Actually, all of the empirically derived MFDs come from other countries. We simply just don't have this data available to us in a usable format that we can estimate these MFDs. And it's complicated by the fact that these MFDs don't look as nice as I showed you in that picture. Often they're subject to these sort of like scattered phenomenon or uncertainty brought about due to instabilities in the traffic networks, hysteresis, estimation errors, things like that. So they don't look as nice and clean. So the goal of this work is to try to come up with a perimeter metering control strategy that sort of accounts for all of these issues and develops a model-free deep reinforcement learning method that can solve this problem without knowledge of the MFD or the underlying traffic dynamics, which turns out to be a fairly difficult to obtain, in a way that's stable, which means that it's able to converge consistently, it's able to learn well and provide a reasonable solution. That's effective, that is at least as good as, if not better than, the state-of-the-art methods, which is the MPC control, and that knows everything, and that's transferable. So it's not an overfitting. We can take the information that we learn about one network, apply it to another network that it's never been trained on, and that it works well. And so our way to do this is, as I mentioned, is using deep reinforcement learning and applying it to this perimeter metering control problem. So for those who are not familiar with reinforcement learning, I'll just do a quick introduction here. To be perfectly honest, I was not very familiar with deep reinforcement learning or reinforcement learning until very recently. So it will test my ability to explain it. So in reinforcement learning, what we have is an agent that makes decisions and learns about the consequences of these decisions to inform future decisions. So we have our agent, the thing, the entity, the logic that's making the decisions. We have an environment, which is the world, okay? And the agent receives some information from the environment. We call that the state. In this case, it could be like, how is it congested, not congested, a measure of congestion, for example. Based on this state, our agent will take an action, make a restriction, a control action, restrict vehicles from entering, let fewer vehicles enter, or let more vehicles enter, whatever that action might be. That action is implemented into the environment, and then the environment changes. And based on that change, the agent receives a reward. And so, like my children, the agent is trying to get as many rewards as possible. You do good things, you get a better reward. So I tell my kids, like, if you pick up your toys, you get more snacks. They're excited about that. If you do a bad thing, like you throw your toys around, like you'll take your toys, so other toys away. It doesn't want to do that. So it can have positive rewards and negative rewards, and it learns from these rewards to make smarter and smarter decisions. Now, the agent isn't terribly myopic, so it looks at not just the current rewards that it's receiving, but it also considers the potential for future rewards. So it looks at like the immediate reward, but can also think long term and say, I can take this action. It might not be the best right now, but it sets me up in a position to get better rewards down the line. And so those future rewards can be discounted. That's a parameter in the process, but just wanted to make sure that's clear. And the agent is not terribly smart at the beginning, so it learns by trial and error. It tries some actions, figures out which ones are promising, and then searches in that direction. Okay, so it'll learn based on the state what types, at the very beginning, it's just completely random. I don't know what to do. I've never seen this scenario before. I'm just going to try anything. And then by trying anything, it'll learn, was that good or was that bad? And then it'll start to learn from that and make more informed decisions over time. So now I want to show how this might be applied to a very simple single region perimeter metering control problem. So imagine that I had that green ring that I showed before. I have just one protected region that I care about, and I don't care about what happens outside. Okay. And so I'm going to show you walk you through the process of this reinforcement learning applied to a single region perimeter metering control. So in the background here, I have this MFD, the productivity is on the y-axis, the network accumulation is on the x-axis. You can see it's a nice MFD here, which our agent does not know, does not see, has no knowledge of, okay? But that's just in the background to show you sort of what's happening that the agent can't see. And so at some point, let's just assume the network is congested. The agent receives information about the current state of the network. Hey, it's congested. Here's the accumulation. It's big, right? There's a lot of vehicles in here. The agent, not knowing what to do initially, tries anything. So maybe the agent says, you know what? Let's let more people in. This is a good, let's just try letting more people in. So the agent loosens up the restriction there, lets more people in, and then sees what happens. Well, in this particular case, if I let more vehicles into the network, I increase the accumulation, and the productivity of the network is going to go down, right? It goes to this point. The agent receives some knowledge of that. It learns that wasn't good, right? So the next time the agent sees this state, if the accumulation is N1, the agent will say, well, the last time, less restriction didn't work well. I'm going to try more restriction. I'm going to tighten up the gates, make more red time. No one can enter. Okay, if I do that, I let fewer people in, the accumulation will go down, and the productivity of the network goes up. The agent sees that and says, oh, that's a good thing to do, right? So, okay, we can do the same thing in the uncongested or free flow side, right? If I have a given state, if it's uncongested, if I try more restriction, of course, the productivity goes down. Agent doesn't like that. So the next time we open up the gates, we let more people in. When it's uncongested, the productivity goes up. The agent likes that. And over time, what the agent will do is learn to move the network, regardless of if it's congested or uncongested. It will learn that this is the optimal state that the network should be operating in to maximize the agent's reward. And so it will learn what to do. When congested, let fewer people in. When uncongested, let more people in. Okay, so that the network productivity is maximized to the best of the agent's ability. Now, that's honestly, this is not a hard problem, right? I just talked you through it. So if I can talk you through it, I don't need a deep reinforcement learning algorithm to solve it, right? That's overkill. But it's good to see that it does the things that we would expect it to do, so that when we apply it to situations that we don't know the answer, that we can trust its ability a little bit more. And so what we did was apply this to a two-region scenario initially. The two-region scenario is kind of like in my world of this perimeter metering control problem. It's like the quintessential problem that we try all of our things on, right? Because it's the problem that we say is we sort of have created as the model problem. That is, okay, this is the one that we're going to try to solve. And so, these are the dynamic equation that's controlling all of the traffic in the background. We have our regions, we have our MFDs, we have flows of vehicles going from one region to the other. In this case, both of the regions are congestible. So if I let too many vehicles, if I restrict too many vehicles from entering one region, they hang out in the other one and congest that one, and that makes the overall productivity go down. And so it's not really clear what to do at any point in time. Actually, that's why we have these complicated model predictive control optimization frameworks to solve it. It's just that those frameworks rely on knowledge of all of these equations and all of these functions. So in our case, the dynamic equations and the MFD are known in our numerical simulations. We're simulating the environment, but the agent has no knowledge of this. We don't give it any knowledge of this, what's happening in the background. It just gets the state and the reward, and that's it. And I'll tell you what the state and the reward is in just a minute, but it's not all of this information. So our inner region is assumed to accommodate fewer vehicles than our outer region. So like a dense inner core surrounded by a less dense suburbs where there's more space for vehicles to circulate. Our inner region has a smaller MFD, means it's not as, it can't be as productive. So we kind of have to protect vehicles going into it, but the outer region it can get congested as well. And so if we restrict too much, that can be a problem. And we simulate a demand pattern that's like a morning peak. Everyone's leaving in the suburbs in the morning, going into the downtown at night for the most part, but there's some cross traffic and there's some, it's not just a one-directional travel, but for the most part, the traffic is is flowing to the downtown area. We call that the morning commute problem for this case. And so if we don't apply any sort of traffic control, any perimeter metering control, what happens is on the right. These are the accumulation in each of the networks over time. The green line is the outer network. Vehicles leave the outer region and go into the inner region, and it just gets less congested over time. The inner region gets more congested over time, and eventually gets so congested it gets more. The accumulation grows so high and becomes so congested, and the productivity of the entire network drops considerably. Now, to make it even more complex, we try to train this in more realistic scenarios, and so. In our cases, we have like estimates of what the travel demand are and estimates of what the MFD look like in the simulations. But the actual demand that is realized during any simulation run has some randomness associated with it. It's just sort of like, we know what the average demand pattern is every day on a typical morning, but on any given day, it might fluctuate, and it can fluctuate a lot just based on some random parameters. So for example, the black line here just shows like the average flow of vehicles moving from region 1 to region 2 over time during the morning peak period, but the orange dots are the actual demand values that are experienced during any time period. Likewise, the MFD, I kind of showed those nice smooth curves. Well, in reality, they're not nice smooth curves. So we start off with the nice smooth curves, but we add some randomness with this so that, on one day, if the network has a certain accumulation, it can be more productive than another day just because of randomness or stochastic behavior. And that's consistent with what we see empirically with these networks as well. We've trained a couple different agents. Actually, this work is getting a little bit more mature now, so that's kind of nice. But we first started with an agent that only took discrete action spaces. So our control variable is, we call it U. It's the control variable that relates what percentage of the vehicles that want to travel from one region to another are actually able to do so. Okay, and again, that's typically can be implemented with traffic signal timing. Around the perimeter of this region, if you want more vehicles to enter, you just let more green time in that direction. You want fewer vehicles to enter, you make more red time. You restrict vehicles and make them wait at the perimeter. So in our discrete agent, what we do is we know what the current control action is, and the agent can just make one of three decisions. It can increase the control parameter, leave it the same, or decrease the control parameter. So it's actually, it makes sort of local decisions. It doesn't just go, it doesn't have like wild swings. It kind of steps its way either up or down, okay? We also have a continuous agent, and in this case, we just allow it to have the whole range of values. Everything's on the table. It can make a little bit more wilder swings, but it's a little bit more, probably more realistic. If you have a very high flow of vehicles going in, you want to just be able to shut it down as quickly as possible. The state itself are the accumulations within each region and an estimate of the demand. So the estimate of the demand is just sort of the black line that I showed there, not the actual dots that represent what the actual demand is, just the estimate of the demand. So in reality, I think we know pretty well on a given day, a typical day, what the average demand might be, or the average demand profile might be for a given, downtown area, for example. We'll never know what the actual demand is. Some days people wake up early and get to work early, and there's less, the peak starts earlier. Some days, everyone sleeps in, or, for whatever reason, doctor's appointments, or whatever, the demand is more, right? So, or less, it can change. We don't know what that is, but we just know what that average is. So we have the accumulations and the estimate of the demand. And in both cases, the reward is what is the productivity of the network during that current time period. One thing I wanted to say about that, if any of you are very familiar with MFD-based work, this trip completion rate is not something that is very easy to determine. If it was, my whole premise that we can estimate these things, we have problems estimating these things would be flawed. But we have really good surrogates for what this trip completion rate is, and that can be something like the speed of vehicles traveling the network, the average speed, or the average flow. We know, we have these good surrogates for this trip completion rate that we can use in practice. All right, so We're going to compare our proposed approach, our deep reinforcement learning approach, with no control scenario, with the model predictive control. This model predictive control knows everything. It knows everything about the dynamics, all those equations that are in the simulation to emulate the environment. The MPC actually has that information. It knows that information. So it's like, you know, it's starting with the best information. It knows everything. Our deep reinforcement learning approach doesn't know that. And then we compare it with our discrete reinforcement learning approach and our continuous reinforcement learning agent. So that was a lot of setup just to get to, I think, the more important part, which are the results. And so what we did was we trained these agents and we compared the performance of the agents, our agents, with the no control case and the MPC case. So this picture here is what's called like a training curve. If you're using any sort of artificial intelligence or machine learning, these systems learn over time. And so in this case, time represents like a day, right? Each unit of time is a day. So, you know, on the first day, you know, maybe our agent doesn't do well, but then it starts learning about this. So the gray line here is the no control approach, right? So the no control, this is the cumulative trip completion rate. That's sort of our estimate of like how well did we do? How efficient was the traffic network at the end of this period? So the no control case is flat. It doesn't change day to day because it's just, there's no control. We don't do anything. The MPC doesn't change from day to day because, you know, this first picture here is just for a purely deterministic environment. And so it's very high. It's better than the no control. So that's good, I guess. And so the green and the blue are what we did. And so I'll start with the green. The green is our discrete agent. And on day one, our discrete agent is really bad. It starts off right here. And on day two, it's bad. And on day three, it's bad. So our agent, you know, again, is just trying random things. And for whatever reason, it does a really poor job. So for a very long time, actually, it does a really poor job. On the scale of like 100 days, it does a really poor job. And then after close to 100 days, our agent starts to learn. He starts to say, you know, making these decisions is not getting me to where I want to go. I need to make better decisions. And here are the better decisions that I need to make. And then its performance starts to improve, and it improves, and eventually converges where our agent can't do any better. Okay, so our discrete agent starts off pretty bad, takes a long time to learn, finally does learn, but the performance is still worse than the MPC. Okay, that's kind of what we expected. Our continuous agent, on the other hand, starts off really horribly. It's actually, it's worse than no control. It's worse than the discrete agent. It's just doing a really, really bad job. But he learns pretty fast. And so from day two, he starts learning the negative consequences of his prior decisions and starts making better decisions. And eventually the performance improves, and then it converges, and actually it gets to be about the same as the MPC, if not a little bit better. Okay, so that's very promising. Now this is in a completely deterministic environment. I forgot to mention before, but these lines, the green line and the blue line, represent the median value of many agents that we train. That like colored space is the range of the agents that we train. So anytime you use some sort of artificial intelligence, it starts off randomly, and the learning process is essentially random. And so we want to make sure that all of the agents, doesn't matter where it starts, it eventually learns. And so it's true, they all converge to a very stable value, even though in the middle, there's some differences in performance between the individual agents that we've tried. So that's good. Learns stably. That's what we wanted. And in this case, actually, the blue line, it learns very efficiently, about the same as the MPC. So we tried this many, many times. We tried it where we varied the amount of error in the demands as we go from, I think, left to right here. We tried it with different errors in the MFD as we go from top to bottom. And consistently, we found the same thing over and over and over. Our discrete agent, not that great, takes a long time to learn, but eventually does, and does a little bit worse than the MPC, which is still good because it doesn't have as much information. Our continuous agent starts off really horribly, learns quickly, and performance is as good as, if not better than, the MPC-based approach. So this is very promising because it tells us that our agents are able to learn, they're able to learn stably, and they're able to learn a control policy that is very effective, as good as the MPC, which has all of the information programmed into it, we're still outperforming that. If we look deeper into what's actually happening, the picture on the right here shows the accumulation in each of the two regions, region 1 and region 2, over time. I kind of lied when I said that we don't really know what to do in the 2-region case. We kind of do, and we've done this for long enough that we have a good sense of what we should do. And what we should do is we should try to keep the networks operating near that critical accumulation associated with the maximum productivity, each individual region. And so when we compare what our agents do to what the MPC or the no control case does, it actually does what it's supposed to do. Region 1, that critical accumulation here is this horizontal line in red, and our agents push the accumulation in region 1. If under no control, it would just get like very, very under congested. It holds just the right number of vehicles in it so that it remains near its like peak operating performance. Region 2, the one that prior got really, really congested, the agents and the MPC approach all kind of keep that operating just about its critical accumulation, which is associated with the maximum maximum capacity or maximum performance in that network. We can look at the control actions from the MPC and our different agents. They have different control actions, but they actually provide about the same performance. And so we kind of compare this, like, numerically. I showed this. This is some of the same information that I showed in those curves earlier, but this is sort of the final information. Again, if we look at the no control case compared to the MPC, deep reinforcement learning, discrete and continuous, these numbers are the total number of vehicles that can complete their trip at the end of the rush hour. So higher numbers are better. And so what we see is that all of the approaches do better than no control. So that's good. That's a good starting point. We compare the MPC with the discrete agent. We see that the discrete agent is a little bit worse than the MPC, about 1 to 2% worse. Okay, it's not great, but it's not bad. It's in the ballpark. And the continuous agent compared to the MPC, actually, we're almost like a 0.5% to 1% better, if not about the same as the MPC. So that's again, really, really good performance. Now, this was tested on a scenario where we really didn't know what was going on. We tested this under different demand patterns where we know the optimal solution. So in an uncongested case, the optimal thing is to do nothing. Like, don't implement any control, set the control parameters to the highest value possible. We tested that. That's what our agent did. It learned to do that. It learned to do it fairly quickly. We tested it in a very congested case where, like, everyone is going from the outside to the inside. And the optimal thing to do is shut it down. Don't let anyone go from the outside to the inside. Like, restrict that to as little as possible. Our agents were able to learn to do just that, do exactly that. So that's that. Again, it's giving policies that we would expect, performance that is as good as the state of the art, but requires much less information, much less knowledge of the dynamics in the system. We then also test the transferability of these agents. So we train the agents on one scenario and then apply them to scenarios that had different starting accumulations, different demands, different MFDs. I have 3 different slides to show you, but I'll just show one, honestly, because essentially what we found is that the blue line is our agent, the orange line is the MPC, the green is the no control, and the blue line is as close to the orange line in all cases. Basically, our agent that's trained on scenario A can be applied to new scenario B without much of a drop in performance. If the accumulations were higher or lower than what we expected, doesn't matter. If the traffic demands were higher or lower than what we expected or what we trained on, doesn't matter. And if the MFDs had more or less error than what we were trained on, doesn't matter. We're able to do pretty well, if not better. Now, everything that I did before was done from the perspective of a computer scientist. I am not a computer scientist by any stretch. I'm not nearly as smart enough, right? So it's basically just applying this deep reinforcement learning to this problem that exists in the transportation world. But fortunately, because we've dealt with these problems in the transportation world, we do have a little bit of information on how, what the optimal policies should generally look like. And so what we did was then said, well, how can we incorporate our knowledge of traffic that's guided by traffic flow theory to help the agent learn what to do? Specifically, what we did was we gave the agent either different starting points or told the agent very specifically what to do depending on certain scenarios. So what I mean by that is we told the agent, look, this box right here, if the networks are really, really uncongested, like it's the middle of the night, 12 at night, no one is on the network, no one's traveling around, right? It's very, very low congestion. Don't do anything. Don't implement any control. Doing it is not a good idea. Like, we know this, okay? I think that's the only sort of thing that we said that with certainty told the agent what to do. The rest of it is we said, hey, agent, like, we don't know exactly what to do, the squiggle, but we kind of are telling you this is our best guess of what to do. You figure it out from there. So what I mean by that is if both of the regions were sort of like in that moderately congested zone, we said, I don't know, man, your guess is as good as mine. Like, start here. If one of the networks was really congested, though, we know that we want to protect that congested network as much as possible. So again, we didn't tell it to absolutely change the value of the control parameter, but we said you probably want to keep it on the lower side. We gave it a new starting guess, and we sort of modified its actions to try to help it have a lower control parameter in those scenarios, but it wasn't allowed to. If the agent found out something to do better, it can do that. Okay, we tried different functional forms. We just basically told the agent where to search based on what we know about congested networks. And it turns out when we did that, we have found some results that were pretty interesting and I think very useful for practical application of this work. So this is the same picture that I showed before. The green line is our discrete agent. I just kind of repeated it here because we remember how bad it was. The blue line was our continuous agent with no human knowledge, and the red line is our agent when we do apply the human knowledge, okay? And what's interesting about this is a couple different things. First, before our blue line, our agent that didn't know anything about traffic was really bad, okay? Actually, its performance was worse than the no control on day one. Now, this is a problem because if someone gave me the keys to the traffic lights in downtown Seattle and said, Vikash, you're in control today, or you're in control for the next month, right? And on day one, I made things worse than when there was no control, they would take the keys away from me right away, right? Even if I told them, I've simulated this a million times, guys, it'll get better. It just might take like day 50. They're gonna say, sorry, dude, like it's not good enough, okay? Like you can't make things worse, like and much worse than they are. But if we apply this human knowledge, actually we start, in this case, it was by design, we started at a really good place. Actually, the performance of the agent got worse over time only because the agent has to search, like it's in its nature to search. And since we gave it such a good starting point, any search was making its decisions worse and worse. Okay, that, we cheated a little bit. But we then tried it on a more realistic scenario. So we said, okay, instead of 2 regions, let's try 3 regions. Actually, we're moving forward to like n regions, right? But let's try 3 regions where there's more control actions, more control parameters, more things that we have to figure out that we don't know. And what we found is if we just let the agent search on its own without any sort of human knowledge, again, it starts off really bad, worse than the no control case. It will eventually improve, but it takes a long time to do it. And it takes actually a good amount of time to get better than the status quo. Once we start incorporating this human knowledge, though, we can almost guarantee that it will never be worse than the status quo, which is great. It'll always be better. And then the agent takes our starting point and then only improves on it over time until it eventually converges. And in our case, again, it converges it to a value that's better than the NPC. So better than the state of the art in the traffic flow modeling right now. So with that, just kind of summarize what we talked about here. I guess I have an animation error, but we developed this model-free deep reinforcement learning and applied it to the perimeter metering control problem for 2 region networks. And we've also done it now for 3 and more regions. The methods use discrete and continuous action spaces. The discrete is kind of useless, so we could probably discount that. But The methods are very stable. They always converge. They're effective. They're comparable, if not better than the MPC method, which has full knowledge of the traffic dynamics and the MFDs and things like that. And they're generalizable, that they can be, work well in scenarios that they were not specifically trained for. This is really nice because it means I can train it in a simulation and then go apply it in practice. It will have to make some changes. It might learn over time, but it can do that without making things worse. The idea is, like, if someone gives me the keys, I don't want to make them take, I want them to take it away from me. So I always want to make sure that it's worse than the no control. And then for implementation, we can use everything that we've done. We've thought about implementation. So all of the inputs, all of the outputs, we have very good surrogates that we could potentially use in practice. It requires no simulations. It requires no, optimization frameworks. It really just requires careful measurements of certain traffic features, and then feeding that into our algorithm, which learns from these measurements, again, getting the rewards, maximizing the rewards, making better and better control decisions. And then that last bullet, I had it bolded, and I guess that screwed up the animation, but the performance can be improved further by adding limited human knowledge. Not a lot of human knowledge, just a little bit about what we know about traffic networks can actually make a huge difference in performance, taking this from something that might never get implemented to something that people might say, hey, let's give that a shot. So with that, I'd like to say thank you so much. If there's any questions, happy to take it now, and really appreciate your time.
Thanks a lot, Vikash. That's very interesting. If you have any questions, feel free to type them in the Q&A box. Maybe when people are preparing their questions, I will just ask my question. It's interesting to see how human knowledge helped in this deep reinforcement learning algorithm. So I wonder, because there are a lot of different human knowledges, right? So how do you summarize that in a way to help this deep learning model to study and get the knowledge?
Yeah, so I was a little flippant about this because any sort of artificial intelligence approaches like this, the human knowledge also comes into the design of the state, the design of the rewards, and things like that. So I kind of joked around and I said, pretend like we didn't know anything, but we did know something. And I have also done some work on deep reinforcement learning for individual traffic signals. I did this with someone who worked in computer science. And I remember the first time they came and they said, hey, we have this amazing algorithm that can optimize traffic all the time. And the first thing I did was I said, oh, why don't we compare it to like a fixed time controller with these parameters? And I just used like a simple Webster's formula and gave it to them. And their fancy algorithm that took like days and days to train and design, like this fixed time controller beat it, that anyone who took like a undergraduate traffic ops class could design, right? And so it was then we said, okay, like it's important to think carefully about what these inputs and outputs are, and we have to select the right inputs and outputs. It's not important. It's not just to say like you can select some inputs and outputs. So that human knowledge comes in selecting the correct measures. That's the first part. But the second part here is the specific type of human knowledge that I kind of focused on was saying to the agent, instead of just searching randomly, which is what any sort of artificial intelligence algorithm is trained to do at the beginning, the very beginning, it's a random search. And then based on that initial random search, it makes more intelligent decisions based on those results. And so our human knowledge was, let's start you off in a better position. When you're first starting, instead of being purely random, let's go with a good guess based on what we know about traffic. And what we know about traffic is when a network is congested, adding more vehicles to it makes it more congested. So if it's congested already, let's try to back off of that. If it's uncongested, we can do whatever we want. People can go in. Actually, if possible, we want to direct people toward the uncongested parts of the network. So let's make your best guess to do that. And so I guess our human knowledge in this case that I focused on was sort of providing that best guess in one part. And then the other part that I didn't really talk a lot about was the functional form about how that best guess is integrated. Okay. We tried a lot of different forms in the agents that we were dealing with. the output of the deep reinforcement learning algorithm is a scalar between -1 and 1. And so we map that to our control actions, -1 and 1 to 0.1 and 0.9. Those are our control actions, 0.1 to 0.9. We map -1 to 1 to those actions, okay? In the no human knowledge, we just do a simple mapping. -1 is 0.1, 1 is 0.9, it's linear, that's it. In our human knowledge approach, we said, okay, well, we know that we want the answers to be lower or higher. And so create a specific function that maps this -1 and 1 to 0.1 to 0.9, but we choose the function that we map in order to, one, make sure the best guess, the initial guess of 0 is associated with actually a specific control action, and how the slope of, how the changing of those control actions change based on the output of the deep reinforcement learning algorithm. So there's two ways we integrated that. I just didn't get into the details, but I can talk more about it if you'd like.
Thanks, Vikash. Another question I have is, you mentioned for the number of regions that the performance difference is different. Like the advantage of the deep reinforcement learning will be higher. But is there like consideration of like the size of the region, the complexity? I know you probably implemented your algorithm in the simulation network, right? So you try to test, the performance and then learn. Yeah, there are certainly more complexity if you have a bigger region, and there are more things inside. How are these things are considered in your modeling process?
Yeah, that's a great question. I think that's more along the implementation lines. I mean, with this MFD-based framework, the region is a region. It can be small, it can be big. I treat it as a region. So what's the most important, I think, about what you asked there is how reasonable is it to model a specific transportation network in this regional way, right? The bigger the network, the less reasonable it is to model it as a single region. And so I like to take things to the extreme, right? The United States surface streets, all the surface streets in the United States, I could say, well, you know what? That's one region. I'm going to model all of the United States as one region, and I can do that. I can do that with math. That will be a completely unreasonable thing to do, right? That's nonsensical. It's not useful. And so it's really, when I go from an actual network to a region, does that accurately model the traffic dynamics? Is it sufficient for my purposes? Am I getting results that are usable? And so I don't know that that's necessarily a question about the deep reinforcement learning part, although I'm happy to talk about it, right? It's just, how reasonable is that? There's been a lot of work on the MFD side by myself and by others, mostly by others, on how do we partition a generic network, a complex network, into these regions. What's the optimal number of regions? Like if I'm trying to balance between modeling complexity, but also accuracy, right? The initial method that I talked about, like breaking it up into all its component nodes and links, that's like taking it to the extreme. Like every link is its own region or its own entity. And the other extreme is I just have one, right? And so the optimal answer is somewhere in the middle. And there are methods to do that. There's sort of these methods that sort of figure out like not only how many regions should we use, but which regions should we use, the network partitioning problem. And so we can apply any of those, and that's actually why we are working on moving this towards N regions, because in reality, a handful of regions may be good enough for like a small city that's fairly homogeneous. But as you get more complex networks, you get sort of more regional dynamics. I can say something like in Washington, D.C., the area around the White House might be more congested than the area near the Marriott, where the TRB is, that's less congested. Or, you get these different regional dynamics where, it's pretty clear, this is a zone that we can treat as one entity. This is another zone that we can treat as one entity. And likely that's more than two. And so we need a method that's scalable, and scaling this up is sort of our next step in what we're going to be doing with this.
Okay, thank you. There's a question in the chat box. So the question is, are there anything to consider for real-world application, for instance, computation requirement for training and implement the model?
Yeah, great question. I mean, my ultimate goal is that someone gives me the keys and lets me try this, right? We're nowhere ready, I'll tell you that. There's a lot of real world considerations that we have to get. So the first thing is we need to be able to accurately estimate these inputs, okay? I certainly have thought about how we can do that. Actually, much of my work prior to this has been estimating these types of inputs and how we can do that. Using probe vehicles, detectors, combining that, camera data. How do we combine point sensors and moving sensors together to get the best estimates of these types of things? So getting estimates of that, real-time estimates of that, are going to be needed because the agent needs to make its decisions based on what's happening on the ground. In terms of computational requirement for training and implementation of the model, actually the implementation is really easy. Once it's trained, it's a neural network. It's there, input, output. There's no latency there. That's pretty easy. It's in the training process that all of the horsepower comes in. We trained this on a simple workstation. Now this was very very scaled down, not a real city, 2 regions or 3 regions, but it can be done on I think existing sort of desktop type computers. As this gets more and more complex, and we have to sort of consider more real world considerations, like sort of doing using some sort of parallel processing to sort of expedite this. And we do this on a graphics card on a workstation for the parallel processing capability in order to make it fast. But we train these agents like in the course of each of those curves that I've shown takes on the order of like an hour or 2. That's because the real world part, we're simulating that numerically, so we can get the real world like fast. So in a situation where it takes a day to get a day's worth of information, there's a lot of information we have to take in, process it, and spit it out. So our goal is to kind of figure out what information do we need to collect, and then how do we do this before we can implement it.
So I see another question. Does the size of the city region matter?
Yeah, that's a good question. I think that's related to your one of your questions, Yinhai, about sort of like again, for me, like a region is a region. If that region represents a small city or that region represents a big city, if you tell me that region represents a small or big city, I am agnostic to that, right? The real question is, does a region, can a small city be accurately represented by a single region? Probably yes. Can a big city be accurately represented by a single region? Probably no. And so in that case, I need to take that big city and split it into multiple regions. How to do that? We have methods. We know this is a problem that I wouldn't say has been fully solved, but is on its way to being solved, or people have worked on it, myself included. How do we take a big region and a big network and breaking it up into the correct regions? We know how to do that.
Okay, so there's one relevant question in the Q&A box. Thanks for the great talk. A following question about the city with multiple regions is that, for example, if the city has multiple regions, do you have any ideas to make them cooperate?
That's an excellent question. So all of the work that I've presented so far has looked at one central agent making the decisions, not individual agents making decisions for the individual regions. But we are working on that. So we've started that. The short answer is we can train them completely, at least our preliminary work, I guess, we can train them completely independently and get results that are pretty good. We believe that by adding some notion of cooperation, we can do even better. And so that's where we're headed towards, I guess. It's work that we are sort of, I guess, just scratching the surface. But it's a great question because it's a great idea and it's something we're trying. I have no definitive answers other than we have tried multiple agents, each agent for an individual sort of region, making its decisions. That's been successful. And now the coordination piece is sort of making sure that they can work together.
Okay, so I don't see other questions. I have another question.
Well, I saw one more. Just want to just address real quick. So the question was like, have you considered congestion outside the region you're controlling? And maybe you just move congestion from the downtown to the outside the downtown. And I want to say thank you for that question because it's a very good question. It also means I did not do my job in this presentation. So I apologize for that, probably just moving too fast. So in everything that we have done, there is no, in the 2 region scenario, there's a downtown and that's one region, and there's an outside the downtown, that's another region. And so yes, we do move congestion from the downtown to the outside of the downtown. However, we absolutely consider the congestion in the outside of the downtown as well. that, I completely understand the question. Sorry I didn't make that clear, but we absolutely controlled considered the fact that there's a downtown and an outside of the downtown. And so all of our metrics were for the entire network, including the downtown and the outside. And so if we made the outside of the downtown operate too poorly, that would lead to a poor overall network performance. Sorry I didn't make that clear before.
Great. So one more question I have is, you design a model and tell the system what to learn and how to learn. So choosing the parameters to learn, I think, is challenging because our control goal is not simply controlling how many vehicles are there. Also for convenience of the vehicles getting into the area. So do you have a plan maybe to put into multiple variables into the domain for the model to control? So you would optimize not just the number of vehicles in the region, but also the real world needs for people to get to the place to do their business or do their shopping, whatever the purpose associated with their trips.
Yeah, so this probably doesn't directly answer your question, but I think one of the things we are doing now also is we're combining this regional modeling scheme with local modeling schemes. So within the regions, I said there's a region and stuff is happening inside, right? But like that stuff that's happening inside is important. And so how do you connect the large scale network-wide approach, this regional approach, with the local approach? We're working on that right now as well. I think your question was also sort of hinting at something related to sort of like departure times or arrival times. Is that what you were trying to get to?
No, I'm just considering, let's say you're like a local region and bigger region, smaller region, how do they collaborate the needs? I think that's important because even in the bigger region, you see the total number of vehicles, but maybe all those number of vehicles is concentrating to somewhere, right?
Yeah, okay.
Your overall control is try to reduce congestion, reduce emission.
Yeah, no, completely understood what you're trying to say. Yeah, I think this sort of we call it a multi-scale approach. This multi-scale approach I think will help to address that because within the regions we just say there's some number, we don't know where they are, we don't care where they're going at this stage. But what we're working on now is how do we coordinate that sort of local level control that, hey, within this region, I actually have a destination and it's over there. And so I need to get there. Well, that requires sort of a traditional traffic control, right? I get to the signal this time, I need to make that move. And so how do we do that? We've done some work, so I've done some work on how to implement adaptive traffic signal control and how that adaptive traffic signal control impacts this regional dynamics. So the relationship from the local adaptive signal control to the regional dynamics. And now we're just like, if I go from local to regional, and now we're just trying to close that gap, regional back to local, and so they can inform each other and sort of have a holistic modeling approach. That would require sort of two, I think, different paradigms. And two, in our case, well, it's actually a really hard problem. And so we're applying deep reinforcement learning for that, but we have two different types of agents, a regional control agent and a local control agent. Those two will have to work together, take feedback from each other, make decisions based on the decisions the other ones are making, kind of, I think, tackle that, like you're saying, like from a microscopic point, yeah, it's not just okay to hold people or let them in, but they need to then get to where they need to go. So that's what we're trying to do now.
Great. Okay, any other questions? If not, consider this Good Friday. I think we probably can return sometime back to you, Vikash. Thank you so much for your presentation today. It's very interesting and hope we could collaborate in the future on this topic.
Absolutely. Well, thank you again so much. I really appreciate the invite and the organization. And again, to everyone here, I really appreciate your time on a Friday, especially a holiday Friday. So I really appreciate it. I hope everyone has a great Easter weekend, and I hope to collaborate with you as well. That would be an honor. Thank you.
Thank you. And thanks everyone, and have a great weekend. Goodbye.